So what I'd like to talk about today is membrane filtration. We'll actually spend the week looking at membrane filtration, and it is the second to the last unit that we will focus on in 483. So when we're looking at membrane filtration, we really divide those processes into two larger groups. Pressure-driven processes, which include reverse osmosis and nanofiltration, and sieving, which includes ultrafiltration and microfiltration. And really, they all require pressure. The difference is that when we're looking at reverse osmosis and to some extent nanofiltration, we're looking at what we refer to as the change in osmotic pressure between what we refer to as the permeate, and I'll go through these definitions, and the concentrate. The theory, I have posted the links to a video really discussing the theory of membrane filtration, actually, and a significant amount of material on really practice, walking you through some videos of membrane filtration plants, in addition to looking at the theory of membrane filtration. So you really want to make sure that you're watching those to get a better sense of membrane filtration. What I'm going to focus on this week is really an overview of membrane filtration and then working through some homework problems that will help, or some example problems that will help with the homework. So when we're talking about membranes, we're talking about these semi-permeable materials. They allow, for instance, water to pass through, but not other solvents or other solutes. They don't allow organic matter to pass through. And the rate of passage is a function of pressure, the concentration of the chemicals that we're looking at separating, and temperature. Okay. And it's also a function of the permeability of the membrane to the solute. Okay. And perhaps in looking at biology classes, you've talked about membranes there. Talk about cellular membranes. Basically function the exact same way that these function, except we're looking at producing much higher quality, or passing through the membrane, across the membrane, much higher volumes of water. So membrane processes are very effective. The problem with membrane filtration is the slow rate of transfer across the membrane. Perhaps some of you have gone backpacking and you've taken a membrane filter with that. And if you have, you know that it takes a significant amount of time in order to filter that water through that, across that membrane. Now, if you're looking at producing millions of gallons of water a day, that's a whole different, call it kettle of fish. That's a whole different issue than what you would do on a camping trip, just simply because of the large surface area that is needed. If you've used a backpacking filter, you may have experienced not only the fact that the flux is low, but also clogging can be a significant issue, especially if there's a significant amount of particulates in the water that you're treating. In fact, often it's suggested, if the water is highly turbid, to actually pre-filter the water through even a cloth, a handkerchief, to try and remove some of those particulates before you pass the water through the membrane filter. Now we're really starting to look here at separating colloidal material and dissolved solids. So these are we're removing particulates that are much smaller than what we can remove, for instance, with sand filtration. The big problem is pressure. These require a high pressure, which means high energy consumption. So that's the challenge with these. This figure gives you a sense of the types of materials that can be removed with various different types of membranes. So for instance, let's start at the bottom with the largest pore size. Okay, so notice it's the lowest pressure. So we're talking about less than 15 psi. But when we're looking at pore size, we're looking at 0.1 to 10 micron pore size. So the larger the pore size, the lower the pressure. And here, if you look at what we're removing bacteria. We can remove Cryptosporidium oocysts. Can also remove Giardia. So most of your backpacking filters are really the low end of the microfiltration, and we typically refer to these as coarse or tight. So tight being this low end and coarse being the larger end of, and this is true with any of these filters. So we can talk about tight ultrafiltration. So notice pressure significantly is increasing. So now we're talking about 15 to about 150 psi. We can remove both the bacteria, shown here with fats. We can also remove proteins, and we can remove some viruses. We can start to remove these, the larger of the viruses. Go to nanofiltration, and now we're talking about 300 to 600 psi. And now, as shown here, we're looking at removing bacteria, proteins, lactose. So for instance, if you buy lactose-free milk, it is potentially treated by nanofiltration in order to remove the lactose. So you can see we're removing smaller and smaller material. Pore size, another order of magnitude lower. So you can think about really each step is about an order of magnitude decrease in the pore size, resulting in significant increases in the pressure, which also means significant increases in the cost of operation. And then we move to reverse osmosis, and now here we're removing salts. So now we would remove bacteria, proteins, lactose, minerals. Typically, if you operate a reverse osmosis system, though, you would typically have some sort of pretreatment. So perhaps pretreatment with a microfilter first to remove the particulate matter, and then removal of the salts with reverse osmosis. And here we're talking about roughly 600 to 900 psi. So here's where we desalinate. A desalination plant uses reverse osmosis. The problem with desalination is we essentially remove everything, which means that the water that we produce is highly corrosive, wants to dissolve just about everything. So we need to think in terms of when we do desalinate, we have to look at post-treatment in order to ensure that we don't have water that is highly corrosive. And again, you can see, again, another order of magnitude decrease in pore size. Any questions about the terminology or the types of filters? This is just another figure, again, trying to demonstrate where membrane processes fit into the overall treatment. So you can see here, we've talked about conventional granular media filtration, sand, anthracite. We're focused there on removing material in the range that's shown here that's really greater than about 3 microns in size. Okay, so that's about the limit of what we can remove. Then when we move to microfiltration, we're looking at this range right here. So we're looking at removing more of the bacteria, may get some virus removal, but you're not going to get much. You'll get some, as I mentioned, you'll get removal of Cryptosporidium oocyst and Giardia oocyst. And then when we're looking at ultrafiltration, now we're looking at removing viruses. We're also looking at removing naturally occurring organic matter. We may get some removal of the larger synthetic organic chemicals, but typically not a significant amount. If we want to remove more of this material, we really need to move down to nanofiltration and coarse reverse osmosis. And then finally, we have reverse osmosis in this region here. This gives us a sense, okay, depending on what you're looking at removing, that's going to determine what type of membrane you use. And that's going to determine the pressures. It's going to determine the energy. It's going to determine your flux. So looking at reverse osmosis, when we need to talk about osmosis. Okay? When we talk about osmosis, we have normally, okay, and they've got a little video experiment that you can watch, but normally what happens is, for instance, here's our membrane right here. And we have on one side of the membrane a less concentrated solution, and on the other side, a more concentrated solution. So what's happened is we have flux of water. So the membrane is permeable to water, but impermeable to the salts in these solutions. We'll have flux until the system reaches equilibrium. So until the concentrations are constant. So one of the things to recognize is that the concentration gradient will play a significant role in determining the flux. In reverse osmosis, we start with a concentrated solution. And what we're doing is we're applying pressure to push the water through the membrane. Notice here, okay, so this is our dilute solution. So what we end up with is a more concentrated solution on one side of the membrane and a very dilute solution on the other side of the membrane. When we're talking about these engineered systems, typically we'll draw a membrane in this way. And what we have is we'll refer to this as the permeate or the product water. That's that dilute, pure or purer water. And then what we have is the reject stream or the concentrate. And that is the portion that we may treat further, but we're not going to distribute. So it is our reject stream. Okay? We need to figure out ultimately what to do with that material. So when we're looking at reverse osmosis systems, we need to know the osmotic pressure of the water that we're treating. And in order to achieve flux through that membrane, we have to have what we refer to as a transmembrane pressure. So the pressure across the membrane has to be greater than the difference in the osmotic pressure
in the feed solution and the permeate.
We're going to model seawater as having a salinity of 35,000 milligrams per liter, and we're going to model it as sodium chloride. And what you're asked to do is to determine the osmotic pressure of that solution. We will assume a osmotic coefficient of 0.85, and that's because when we're looking at these solutions, at the concentrations that we're dealing with, the solutes don't behave ideally. What does that mean? It means that they interact with one another. And therefore, we have to use this essentially correction factor, this osmotic coefficient, to account for that. So the osmotic pressure is equal to which are the number of ions in solution. So for instance, with sodium chloride dissociates to form sodium plus chloride. So in this case, I is equal to exactly 2. On the other hand, if we have sodium sulfate, I is equal to so instead of a sodium chloride solution, we had a sodium sulfate solution. So in that case, I is equal to exactly 3. So we have 2 sodiums, 1 sulfate. So I is equal to 3. Okay. Phi is our osmotic coefficient. C is the concentration of the ions in solution. R is the ideal gas law, and T is temperature in Kelvin. So we have a solution, 35,000 milligrams per liter of sodium chloride. The osmotic coefficient is 0.85. Temperature is 15 degrees C, and that is 288 Kelvin. Okay. So the osmotic pressure of this solution is 2 times 0.85 times 35,000 milligrams per liter divided by 58.5 milligrams per millimole. That is the molecular weight of sodium chloride times 1,000 millimoles per mole times the ideal gas constant, 0.082 atmospheres liters moles degree Kelvin times 288 Kelvin. And let's just check the units. Milligrams cancel, liters cancel, millimoles cancel, moles cancel, Kelvin cancel, and we have an answer 24.0 atmospheres. Which, if we multiply 24.0 atmospheres times 14.7 psi per atmosphere, that is equal to 353 psi. Okay, we need to exceed that in order to treat this. Now, notice, if we raise the temperature, what happens to the osmotic pressure? Raise the temperature, how does that impact osmotic pressure? Exactly, it increases. Which means our transmembrane pressure also will have to increase. Energy consumption will also increase. So that's an important thing to remember when you're designing these systems. And just to kind of give you a sense here, okay, we're looking right up in this range here in terms of pressure. Now, the flux of water, okay, is a function of this coefficient of water permeation, and that's a function of the membrane. There has been significant efforts made in the recent years to increase this. Why? Why would there be significant efforts made to increase the coefficient of water permeation?
Because then your membranes can process more water.
Exactly, because then your membranes can process more water, which means it's less cost per volume of water treated. And that's important. Delta P is known as the transmembrane pressure. So that's the pressure differential across your membrane. And delta pi is the difference in the osmotic pressure, again, across the membrane. So we're looking at the difference between the feed solution, that's your influent, and the permeate, that's your product water. The solute flux, now we're looking at the salt, okay? And this is really particular with reverse osmosis, where you may get some, or you will get some leakage of salt across that membrane. And that is a function of what we refer to as the mass transfer coefficient for the solute flux. Now, what that means, okay, this K sub S, and it's a function here of the diffusivity. And that's the important thing too. Okay. So K sub S is proportional to the diffusivity of not of the water, but of the solute that you're trying to remove. So that means, okay, that as diffusivity increases, the flux of your salt increases. What does that mean? Solutes that typically have a higher molecular weight will have a higher diffusivity. Oh, sorry, will have a lower diffusivity. So as molecular weight increases, diffusivity decreases. Okay. However, as temperature increases, the diffusivity also increases. So how does that impact removal of ions? And that's really what we're focused on when we're looking at reverse osmosis. So let's just think we have sodium versus, let's do lithium, sodium, potassium. Okay. Molecular weight is increasing. So which of these would you expect to have the highest solute flux? So we have lithium, sodium, potassium. How does diffusivity vary with those salts, or those ions are not salts, those ions? Or how does molecular weight? Molecular weight's increasing. So which has the greatest diffusivity? It's Monday. Okay, so lithium has the greatest diffusivity, which means that if we're looking at the flux of the salt will be greatest for lithium, then sodium, then potassium. Okay. So that's important, and it's also important to also remember that this is also a function of temperature. So as we increase temperature, diffusivity increases, which means we're going to have a greater flux of salt. We'll talk about this later in terms of what we refer to as rejection. So when we talk about flux of salts, we typically talk about percent rejection. Okay. So let's look at this problem here. We have a high pressure reverse osmosis system. It's being evaluated to produce pure water from seawater. It's to be blended with seawater, so it's going to be blended with some seawater that will, after treatment, increasing the salt so that it's less corrosive. And you're asked to make an order of magnitude estimate on the required pressure differential if the difference in osmotic pressure must be 2,500 kilopascals. You're told that the mass transfer coefficient for water flux is 6.89 times 10 to the minus 4 meters cubed per day per meter squared of membrane per kilopascal. And you are also told that you want to produce that the flux of water is 170 liters per hour per meter squared. So that's our flux of water. Okay, it's a volumetric basis. So we have 170 liters per hour per meter squared. kW is in cubic meters, so we need to convert 1,000 liters per meter cubed. And we have 24 hours per day. Hours cancel, liters cancel. We've got meters cubed per meter squared per day, and that is equal to 6.89 times 10 to the minus 4 kW, meters cubed per day per meter squared per kilopascal. And we're going to multiply that by delta P minus the difference in osmotic pressure, which is 25. That's 2,500 kilopascals. Okay. So if we solve this, we're going to solve for delta P, and delta P is equal to 8,420 kilopascals, or about 1,200 psi. So we're talking, you can see here, very significant pressures, which means very significant costs to treat this water. The next part of this problem asks you to calculate the mass flux of solute. Again, we have an influent concentration, so here's our membrane. And this is really the membrane system. This is not the membrane for this size system. But we have 35,000 milligrams per liter. Our effluent concentration is to be 0 milligrams per liter. And you're told that your mass transfer coefficient for the solute flux. So now you're looking at for the sodium and the chloride. And that is equal to 6.14 times 10 to the minus 4 meters per hour. So the equation that we have is the flux of salt is equal to the salt permeation coefficient, or the mass transfer coefficient for solute flux, times the change in concentration across the membrane. And that is equal to 6.14 times 10 to the minus 4 meters per hour times 35,000 milligrams per liter minus 0 milligrams per liter. We're asked for this in kilograms per day. And that is kilograms. We have 10 to the 6 milligrams per kilogram. We have 1,000 liters per cubic meter. And we have 24 hours per day since we're asked for it per day. So let's just check. Hours cancel, milligrams cancel, liters cancel. We have meters here, meters cubed there. So we have meters squared. So we've got kilograms per meter squared per day. And that, once we solve that, is equal to 0.52. Okay, so that's the amount of salt per meter squared of membrane per day. That is how much that's our flux of salt. Or solute or salt. As I mentioned here, we talk about rejection. Yeah. So we're looking at the concentration in the permeate stream and the concentration in the feed. So let's say here we have 350 milligrams per liter of salt or sodium chloride in our permeate stream. Okay. We had 35,000 milligrams per liter in our feed stream. So 1 minus 350 milligrams per liter divided by 35,000 milligrams per liter times 100% is equal to 1 minus 0.01 times 100%, which is 99%. Okay, so 99% may sound like really good removal, but we still have 350 milligrams per liter of salt in our solution. So you can imagine when we're looking at really pure solutions of really pure water in our product stream, we need to achieve significantly greater than 95% rejection. Now, recovery is, as we said, what we have. Again, remember, this is not a single unit. This is the system. But we have our permeate or our product flux, and we have our reject, and we have our feed. Okay. The recovery is the concentration of our permeate flux, or recovery is the permeate flux divided by the feed flux, so our flow rates. So we're looking at flow rate of water, that is our product water, divided by the feed water. And typically you're looking at, depending on the membrane, depending on the pressure, the transmembrane pressure, somewhere between 35 and 75% recovery. Now, newer membrane may be able to get greater recoveries than that, but we're still looking at relatively low recoveries compared to most other processes, which means you're treating significantly more in order to obtain the flux that you need to distribute. And that's an important thing to remember. I'm going to stop there.